Hello and welcome back to Calculus 1, section 3.7, the infamous chain rule. The most important, the most frequent derivative technique, because the chain rule is the derivative of function composition, and most of your functions are function compositions around. Because rarely function is just the basic function. It's always modeled with some kind of a function composition, pretty much, and this is the way to take the derivative of the function composition. Therefore, it's probably the most important thing you are going to learn in Calculus 1. It will be used in Calc 2 and Calc 3 and everywhere else. You'll have multivariable chain rules in Calc 3. So yeah, let's see how this works. So what is the difference between sine x and sine x cubed? Obviously, the cube part, right? But the thing is that this over here is the basic function, right? I like to call that vanilla, where this over here is a function composition. And what is a function composition? Well, function composition of f with g plugged inside of f. Now, I know that I talked about this on the first day. You guys did have function composition on your first exam because, again, we talked about it and you have the entire lecture on it in Pre-Calc 1. But now you actually have to use this. And because you have to use it, we're going to have this, what I would call the final review of the function composition. So f composed with g of x is also known as f of g of x. And technically what it means is plug g of x for every x of f. Plug g of x into every x of f of x. So if I have my f of x to be x squared plus x minus 1 over x plus square root of x minus 3, and g of x is equal to cosine x, what is f of g of x? Well, this thing here clearly said plug g of x into every x of f. So I will be replacing all of these x's by g, and g is cosine. So we'll have cosine squared x plus cosine x minus 1 over cosine x plus square root of cosine x minus 3. There's a function composition. Now you can make this prettier by writing this over here as the secant, but you can't do much past that, so I'll point the arrow and I say secant x, but whatever. The most important part is to understand that this cosine, which is a function, went into every x of f. Now we can have this backwards as well. We can have g of f of x, in which case this is the boss function, and the upper function plugs in it, so it will be cosine of x squared plus x minus 1 over x plus root x minus 3. And that's if you go at it from the other angle. Now, for calculus, we are not necessarily interested in composing functions. we are actually interested in decomposing functions, which is something you haven't done much of in pre-calc course. So decomposing functions, meaning what is the meaning of e to the x squared? Like, what does that mean? And you go and say, it is actually my main function f of x is e to the x, and then the function that I plug inside is x squared. Because when this replaces this x over here, I get e to the x squared. So this is what we need, guys. This ability to mentally break this down into components, because we will be taking derivatives of every one of these steps separately. You'll see that. Let's have another example. How about 4 cosine of x plus 6? Can anyone tell me what is the main function and what is the one that it's plugged in?
It's f of x is your main, and then g.
Yeah, what are they in
f
terms
of x is cosine, and then
oh, sorry, yeah.
X plus 6.
Okay, I heard x plus 6 over here. What do I put here?
Yeah, cosine.
4 cosine x.
Aha.
Oh.
I don't know why I stopped at f of x. Brain fart, but.
So it will always be f of x over here and g of x on the bottom. Okay, that's fine. Let's go. Let's go. We have a lot more of these. There is more where all of this came from.
Is 36 over x plus 9, and g of x is x squared.
No, I would have had 36 is f, and then g is 1 over x squared plus 9.
I like the 1 over x part over here, and then x squared plus 9 over here. Or, I mean, for the purpose of derivative, you could do it, but it's not correct from the perspective of composite functions, but for the derivative would actually work.
So you
1 over x plus 9 and then x squared. It could work, but this is still composite function because that one could be then written as 1 over x and then x plus 9 and then x squared again. So that will just make more mess. So I would just go with the first one right here.
Okay.
You want to have a basic function on f, okay? That's the requirement. And 1 over x is basic. I mean 4 times, who cares? This is gonna jump out in a derivative anyway, so whatever. Oh, where's my 36? Holy nightmare. There we go. So you want to have the basic function on the x line. All right, let's go. There is more. There is more. Where did this come from? So how about, let's do the easy one.
F of x is root x.
Perfect.
And g of x is 3 minus x.
Excellent. That's a cheap one, right? That's a cheap one to decompose because we can see this. Okay, let's open the gates of hell. See what's cooking inside. Still pre-calculus. Can we do this in 2 functions?
No, you can't.
Exactly. Now we need 3. FGH. And
would F be sine x, and then G would be x plus 9, and H would be 3 sine x, or something like that?
you can have sine on 2 of them because you have,
okay.
right? Let's think of this
Would
as
it,
layers of the onion, guys. And remember what this square does.
Oh.
It's 3 times sine x plus 9 squared. See if when you use algebra to rewrite the function, it might help you reorganize these in your head. Think about it.
Is it f of x being 3x squared?
Yes! Awesome.
Oh boy, he was so happy. Then I have g of x is sine x, and h of x is x plus 9.
Nice. Yeah. All of this you need to practice, guys, this until this is just common sense in your head. This is not the skill we are teaching, right? This is the pre-calculus part. We are teaching to take the derivative of this. And in order to take the derivative of this breakdown here has to be clear in your mind so that you can take derivative in appropriate, what we call chain, right? So that you can have all of the terms present. So now that we are at this, let's let's keep digging. So 4 ln cubed of square root of x minus 6. Just because I can. This is complete garbage. It models nothing. This is just one of those, look, ma, what I can do.
So is it 4x cubed for 1?
Yes.
Then the natural log of x squared? Oh, x to the 1/2?
Nope. Just ln, right?
Oh, okay. And then x minus
Because
6.
this cube will come out right there, right? And then when you peel off ln, then you have a square root.
Gotcha.
And then r of x. And we ran into the 3 level, 4 level actually, function. I have 4 levels to dig in. As I said, I have never seen anything like modeled with anything like this, but for the sake of, yes, I can do this, here we go, right? Now, the most famous and used cases are cosine 3x, e to the 6x, e to the negative 5x, tangent, I don't know, 4x, whatever. And then obviously, you know, x plus 9 cubed, and ln of x squared plus 1, let's say. All of these are composite functions. And all of these here are only with f and g. They only have 2. Now, are you going to have the ones with 3? Here and there, yes. With 4? Well, that's really if I want to try hard, right? You're not going to see probably any one of those with 4, like this ln problem here. By the way, note that this notation on ln cubed is following the same rules like a square on a sine. So it would be written right this way, except it's a ln problem. So make sure you have that. And all of these are composite functions, and all of them are f of g, where you can think of what's inside, what's outside, what's the inner function, what's the outer function. You can also think of it as layers of the onion, where you are peeling the layers off to get, to this most inner function. In this case, it's only one layer of onion that you have to get off, which is this x cubed around it. So for some of you will be easier to think inwards, and for some of you will be easier to think outwards. It doesn't matter which way you think. It matters to you, obviously, because you understand it that way. But you have to have one of those make sense. So whether you're going to think outwards, which is, right, you start inside and you go out, or you are recognizing what is the outer function and then you pull in. Whatever. It's just they have to have exact order, right? So the order cannot be changed. So it is F and then G and then H and then R. Whether you wrote it going up or going down, it doesn't matter to me which way. It matters to you, right, to get it right. But you cannot swap any of these in their order. But when you need to write them up, as I said, you can go this way, you can go that way, whatever makes visual sense to you as you go in. Now, I will just let you know in advance that my personal is going this way, because I am able to see the outer function and then step inside and step inside and step inside. But I've met plenty of people and some of my colleagues that go this way. So there is no right or wrong way to do it. As Nike would say, just do it, okay? Now, finally, we are there to talk about the chain rule. The way to take derivative of composite functions. And here we go. The derivative in respect to x of f of g of x, composite function, is the derivative of the outer function, g is still plugged in, times the derivative of the inner function. So that's the formula. We can write this formula in a chain form as the derivative of f of g of x is equal to the derivative of f in respect to g, and then the derivative of g in respect to x. Now, it is perfectly fine for you to go, what the hell is this? We did not take the derivative in respect to the entire function. Well, that's correct, and you will never take the derivative in respect to a function. But if you just want to learn this from a perspective of basic variables and letters, let's quickly take a look at sine of x squared plus 1, because we decompose that as sine x, which is your f, and x squared plus 1, which is your g. Would you all agree that this is just sine of g? If I do that substitution, instead of x squared plus 1, I put a single letter g, then all of a sudden, df dg makes a lot of sense because that's just cosine g, right? Derivative of sine is cosine. So then this part here makes sense because we just use the substitution. And now your function is no longer in terms of x. Your function is now in terms of g. So the sine g is the new sine x, and the derivative of sine g has to be cosine g. And then you have this extra piece, which is called a chain. That's the chain part, which multiplies this with the derivative of g itself, which is 2x. So now, what is the derivative of sine x squared plus 1? Well, the derivative of sine is cosine, and you have to keep function plugged in. And then multiply that by the chain, which is 2x. Now I'm going to write the formula on top of this. This is your derivative of f with the g plugged in, and that is equal to the derivative of f with the g plugged in times the derivative of g. This over here is usually the hardest part. Do we all see that this is g? Do we all see how derivative of sine is cosine? Derivative of sine g is cosine g. You have to have g plugged in. If you have a question, now is time to ask. Not in 15 minutes, not in 2 days. Now. The derivative of e to the 3x. Well, we said that derivative of e to the x is itself. So I'm going to take the derivative, get 3x, and then multiply it by the derivative of the exponent, which is 3. I hope you now see where that formula with a is born. 3e to the 3x. So we are able to make that into a formula. I have my f, which is, let's use blue. I have my f, which is e to the x. I have my g, which is 3x. When I took the derivative of f in respect to g, I got e to the g, but g is 3x. So here is my derivative of f in respect to g, so g is still plugged in, and then the derivative of 3x is just 3, creating this, which actually gives us that shortcut formula, so we don't have to go through this calculation if you know the formula, which just drops a in front. A little bit convoluted, and this really gets better with time and with insane amount of practice, especially if you're lacking skills with function decomposition. All right, so I'm going to ask you to tell me the derivative right here. So try it, practice it, see. We still have only two functions, right? You have the outer function and the inner function, so it's only f and g. You don't have to worry about anything else. What would be the case for this derivative?
Professor,
Yes?
I'm not sure if it's completely simplified out, but I think I have it.
I just need the first step.
Oh,
Simplification we're going to practice later with factoring and all of that stuff. I just need that first step to make sure that you guys are actually understanding what goes where.
so you mean like the f prime of g times g prime step?
Yes. That one.
I have
The big guns.
six to the quantity, or 6 times the quantity, 3x squared plus 4x, all of that to the fifth,
Yes.
times 6x.
Excellent. That's it. And now I'm going to actually, that's perfect. So now 6 times 6, 36x in front, and you're done, right? I'll write it. So 36x and then 3x squared plus 4x to the 5, you're done. So if you have this in your notes, that's 100%. And you can't go, I mean, you can factor out an x and then to the 5, and then with this one will be x to the 6, and that will simplify. But I just want to point something else out. So this is perfect. Good job. Now let's take a look at this. The way I do most of this in head is like this. What I see is technically some x to the 6 over here. Do we all see that f is x to the 6? At this point, I have to say you better see that this is x to the 6. And then g is the one that it's plugged inside, like that. Right? So this is what I say. I technically have x to the 6. What is the derivative of x to the 6? It is 6x to the 5. So this is that x. See, it's x to the 6, and the derivative of x to the 6 is 6x to the 5. So I hope that you see that x to the 6 jumps into 6x to the 5. Now this x inside was this entire mess. So that's what I am going to plug in. This 3x squared plus 4x. And then I take the derivative of the inside, which I copied. Oh, it's 6x plus 4. It's 6x plus 4. Because the derivative of 3x is 6x, and the derivative of 4x is plus 4. So it's actually 6x plus 4 in there. So this over here, we can leave it as 6 times 6x plus 4. Okay, it's fine, it's fine. Fixed it. And we have it. It's done. I'm going to show this method again. This is like a visual method to do the problem. Let's say you have 4 cosine of 3x squared minus 1. And you want the derivative of that. What I see is 4 cosine x. So what is the derivative of 4 cosine x? All of this thing I mush into this x that it's on the bottom. So all I see is 4 cosine x. What is the derivative of 4 cosine x? It's negative 4 sine of mess. I actually use word mess in my head. I have 4 cosine of a mess. What is the derivative of 4 cosine of the mess? It is negative 4 sine of that mess, which is how I know to copy 3x squared minus 1. Anytime in my head I say mess, that's the mess, right? The stuff that it's in there. And I will actually let you also know why I use the word mess. And then the derivative of this is your chain, which is why it's called the chain rule. The derivative of the inside is 6x. For the total of negative 24x sine of 3x squared minus 1. Now, why do I call this mess? It's because when I learned function composition for the first time, I looked at it as the professor in class, the teacher in class, used the word box, but I used the book bag in my, because book bag was something that I could just see, because you can put the stuff inside. So you have the book bag, and the function of the book bag is to carry, let's say, books. And the books have function, you read them and learn from those books. So if books have function, book bag has a function, and you plug one function into another, which is literally putting the books inside the bag. But the bag is going to have also all other mess. This is where I picked up the word mess, because you're going to put a whole bunch of other stuff in the bag, not just the books. And it becomes messy, right? When you have a whole bunch of stuff, and especially if you don't clean it every week or something. So it picks up a lot of mess inside. So you can say, okay, money has a function, wallet has a function, bag has a function, so I put money into the wallet, wallet into the bag, and then I have the bag. That's like a three-step function, FGH, because money is in the wallet, wallet is in the bag, and the bag contains the money as well, right? So here is the bag, here is the wallet, here is the money, right? Going out. So that's one extra. So money into wallet into bag. Now, if I want to change the property of the bag, I put in a parachute inside, and now it becomes the bag with a parachute. So I can take this bag and jump out of airplane with it. It's not going to be good if I jump out with a book bag, right? Because it doesn't have a parachute. But if I jump with the one with the parachute, so the function together changes, the function of the entire thing changes with its content, and the content was provided whether inside is a book or a parachute. And I can use now the same bag and put inside the camping equipment and go camping, right? So the content of the function that you place inside the bag changes the function of the bag, right? So that's something that it's important. And then I said, okay, so if I have a bag over here which holds books, I take the derivative of that bag, I painted it or something, I changed the appearance of the bag, because that's what derivatives do, they change the function, right? I still have the same books inside. So I copy the mess. I don't know, somehow in my head that made sense, and I just learned it that way. So take the derivative of the outer function, copy the mess inside, and then take the chain, which is the derivative of that inner function that was stuck inside. Somehow that makes sense to me. Here is another one. This is going to be, let's say, 10 square root of 1 plus tangent x, because we can, right? So how many functions do I have? It's again just two. There is 10 root x, which is the outer f, and then there is the mess that it's plugged in, which is 1 plus tangent. So that's how my head works. Whatever works in your head, it's fine. You just need these building blocks so that you can do the rest. And then I say, aha, what is the derivative of 10 root x? Well, I know I have to copy 10. Then maybe you memorized that the derivative of root x is 1 over 2 root x. Maybe you memorized that, maybe you didn't. Right? I can't help there. It was there in the lecture 3.3. So this was in 3.3, and you either know it or you don't. And as I said, I can't help that. So when I'm taking the derivative, I know how to take the derivative of x, but I need to keep the mess inside, right? So it's 1 over 2 square root of the mess, and the mess is 1 plus tangent x. and then the chain, take the derivative of the tangent. Derivative of 1 is 0, and then the derivative of tangent is secant squared x. Now 10 and 2 will cancel, so it's 5 secant squared x divided by the square root of 1 plus tangent x. It looks terrible to the untrained eye, but when you practice this enough, it becomes the second nature, especially that well over 90% of all derivatives you ever take from today on will be chain rule. And as I said, this effectively ends your education in calculus if you can't figure this out, or if you don't want to figure this out, or if you are skipping this section because you had the exam last class and you're taking a break and then you'll pick up calculus next week and you missed this. There is no calculus in the future without this, because your functions are never just ln x and e to the x and sine x. That's very, very rare, even for math exams and math problems and so on, going on Calc 2, Calc 3. It's very rare to use what I call a vanilla function. Everything, maybe 99% of your problems in the future will be composite functions, and this is the only way to take the derivative of the composite function. So if you don't know it, you can't do anything. Which is why I hope that you will join for office hours, that you will ask questions, that you will do all of the problems in homework, even though only 5 are required. You will do all of them because you want to learn this, because I said that if you don't learn it, you're done. And it's not a threat, it's a fact of life. That's, I mean, fact of calculus, fact of life. Yeah, fact of life, it's good. Let's take a look at some of the homework examples. And as I said, we're going to pick up with this. We only have about 15 minutes left in class. After this, I have office hours. If you want to join in for exam and stuff, that's fine. But let's take a look at the problems that are given in the homework. And then I'll hint something for the next class, you know, with the problems we're going to do. So let's take a look at some of the random stuff. So I'm just going to poke somewhere in the book without looking, and I landed on problem 35. Great. It says the derivative of tangent of e to the x. All right. I'm going to give you 18 seconds, and then I'm going to kick in. So no rush. You have 18 seconds. Yes.
Is it secant squared x times tangent e to the x times e to the x?
I don't think you would have another tangent in there. It should not have a tangent.
Isn't that what you throw into the...
The tangent is outer function, and the derivative of tangent... Well, we'll learn it today, so it's okay to make a mistake, obviously. The derivative of tangent is secant squared, so the tangent will not repeat.
I see. Sorry.
All good. Well, there's no sorry. You are learning. Relax. It's all good. It's infinitely better to participate and make a mistake than not participate and not learn at all. Because if you're, as I said, if you're just watching this class as a movie, you're wasting your time and your money because you are not learning. That's simply what it is. Anyway, any other suggestions?
I got e to the x secant squared e to the x.
Yes. So we have our f to be tangent of x, whose derivative is secant squared x. And we have our g to be e to the x, whose derivative is e to the x. So the derivative of the outer function is secant squared of the mess, and the mess is just e to the x, times the derivative of whatever was buried inside the secant, which is just e to the x, which is itself. So as you said, e to the x secant squared e to the x. So that's problem 35 in a textbook. Again, I'm going to poke my finger into random problem and land on 42. The derivative of cosine to the fourth, or they use theta, so d theta. Cosine to the fourth theta plus sine to the fourth theta. All right. Do we see that these are completely two different problems? Two
Yes.
Yeah.
separate chain rules. So sine has nothing to do with cosine. If this was cosine to the 4 of sine to the 4, then they are nested and together. But cosine has its own argument theta, sine has its own argument to theta, so these are two completely separate functions. So I will have the world of chain rule here for cosine and the world of chain rule here for sine. If we are good with that, the next part that some people might have issue with is that this cosine should be actually written as cosine theta to the fourth. So we are talking theta to the fourth and then cosine theta plugged in. So the outer function is actually that x to the fourth. So let's see. Drop 4, put the mess cubed, and the mess is cosine theta, and then take its derivative, which is negative sine theta. Plus, that's the plus, and rinse and repeat for sine. Again, it's like 4x, x to the fourth, and the derivative x to the fourth is 4x cubed. Now the mess in here is sine theta, and the derivative that in a chain is cosine theta. And now we can, do the best we can to make this a little bit prettier because chapter 4 is coming. So negative 4 sine theta cosine cubed theta plus 4 sine cubed theta cosine theta. And all I'm going to do now is an additional flex, all right, to simplify this a little bit because we can kick out 2 sine theta cosine theta from all of these. Now, why am I kicking this out? Because it is a special formula for trig. And what's left behind, I'm going to swap the terms, is 2 sine squared theta minus 2 cosine squared theta.
Is that the double angle formula for sine?
Nice. Sine 2 theta. Very good. Now over here on the second part, additional flex, where I'm going to factor out -2, which would leave me with the cosine squared theta minus sine squared theta. The hell is this now?
Isn't that your Pythagorean identities?
Pythagorean identity is with plus, and it's equal to 1. But when it has a subtraction like this, it is this thingy with a cosine, double angle. So sine 2 theta times -2 times the I should have put -2 in front. So -2 sine 2 theta cosine 2 theta. The grand finale. Anyone? What is that? We had it already. Come on. It's right there. Same. So now, do you want to set this equal to 0, or do you want to set this equal to 0? Welcome to chapter 4. Right? Now, dealing with these trig identities, as I said, that all depends on, did you learn it to learn it, or did you learn it for the grade and then forgot it, right? Which is pretty much the rest of mathematics. Let's see if we can have an example that does not have trig in it, because everything was trig so far. Yeah. All right, so let's switch the story here and talk about if it's interesting or not interesting. Problem 50, still the same homework, obviously same section, but the derivative of x over e to the 3x. What kind of problem is this?
It's a chain rule inside of a chain rule.
You started it well, and I was about to jump yes, but then you said chain rule again.
There's a quotient.
That's the one. It's, everyone, please look at the screen. This is, I'm going to say it and circle at the same time. Ready? It is a chain rule inside the quotient. Chain inside quotient. So you do the quotient first, and when you are taking the derivative of e, the chain kicks in. All right. What do we have now? We have chain inside the quotient, quotient inside the chain, quotient inside the product rule, which is the chain rule with something else, and so on. We can make this, you can't make it hard, you can make it insanely annoying. There is a difference between hard and annoying. Once you learn the formula, once you understand the concept, it's no longer labeled hard, but then you are going to see a problem like whatever, 64, and you're going to say, oh, it's annoying. There's the big difference between annoying and hard. So here we go. The chain rule, sorry, the quotient rule. Take the denominator and square it. Then copy denominator as is, the derivative of the top, minus copy the top, and this is where the chain goes. So now this is your, you copy e to the 3x times the chain rule of 3. Now obviously if you remembered your a e to the ax, you can use that instead, right? You don't have to go and do the chain rule if you know the formula. But if you don't know the formula, you do the chain rule. Whatever. All right, so now we're going to go and say e to the 3x minus 3x e to the 3x. Now, I could write e to the 6x on the bottom, but I'm not going to. I'm going to write this because one of them will cancel when I factor on top. So one of these cancels, and that's it. You're done. The answer is 1 minus 3x over e to the 3x. And you will say, why? Because this is a position function, and now it's velocity. Because it's a population model. Because it's garbage decay. Because it is needed to calculate the change, the rate of change of something. That's why. That's why. And your nature functions are more likely to look like this than to just look like sine x. So that's something that you have to now understand and work with. All right, one more problem quickly, and I'm going to switch to office hours. Those of you who would like to talk to me about anything, please join there. We are going to take a look at execute order 66. Again, if you don't know what that meant when I said it, you are in a wrong class. Not the instructor, just calculus and STEM. Tangent of x e to dx. If order 66 means nothing to you, I am really puzzled why you're in this class. Why are you in STEM? I'm biased that way. What can I say? Anyway. There's the problem. What do we have as a mix in here?
You have a product and chain.
Thank you. Product in the chain. Product inside chain. So chain is first to be done, and the product will be done when we have to. So if the product is inside the chain, then chain rule is the boss, and the product will be done whenever we have to do it. So the derivative of the outer function is the tangent. Tangent is outer function. The derivative of tangent is secant squared of the mess. And now comes in the chain, and that's the product rule. Copy the first, derivative of the second stays the same, plus copy the second, derivative of the first. So you did your chain rule. This is all chain rule. That's a chain rule. But the mess inside was actually the product rule, so that's why we have a product rule inside the parentheses there. So this is going to be, we factor out e to the x, then you have your x plus 1, then you have your secant squared of xe to the x. And now you can set this equal to 0 for chapter 4 when it's simplified like this. Get no solution over here, get x equals -1, and then also no solution over here. So the whole thing is -1, then you have your critical point, then you can look for min max and do the rest of chapter 4. Simplifying these is important, factoring is important. Again, if you don't learn it and get in a habit now, then you will eventually in chapter 4, because you can't really solve this equals 0 right there. It's just harder. You need simplified version. And that's it. We are done for the day. I hope to see some of you stop by office hours today or Monday or whatever. We can talk and chat and figure things out, especially if you have questions.
Your Monday
We'll
office
see.
hours are at 5:30, right?
I hope so. Yeah, I think so. I get the phone notification. Let me just end the stream. Bye, stream.